Hello, Chem 213 students, and welcome back for this week's lectures regarding Chapter 17, Aromatic Compounds. There's going to be two parts to this lecture. This is a bit of a shorter chapter for this week, and we're going to go ahead and get started talking about aromatic compounds here. What you see in the background behind me is a picture of graphene, which is graphite, which is aromatic rings of carbon stacked on top of each other. So this is like your pencil lead here. So aromatic compounds, their name derives from the fact that they were originally isolated from fragrant oils, but it's kind of an anachronistic name now. What defines them is not really their smell. Most of these aromatic compounds actually don't have a smell, like benzene, for example, or they smell like gasoline or something. Smell particularly good, a lot of them. But a lot of compounds, a lot of different compounds contain aromatic rings and do actually have a pleasant smell. These include benzene here. This toluene is methylbenzene, essentially. It has its own special name, toluene. Also, there's special names for dimethylbenzenes called xylene. And then depending on where the second methyl group is, they have different prefixes here. And we'll talk about all of those namings in a moment. But these are three examples of benzene and benzene derivatives. You can see that benzene rings or aromatic rings are very omnipresent in nature and also in a variety of drugs. So these are a selection here of various drugs that treat all kinds of different conditions from acid reflux to depression and so forth. So you can see that it's very common in many organic structures to have aromatic rings. Coal. Coal is a compound that contains plenty of aromatic rings. When you burn coal, it makes products that also still contain these so-called polyaromatic hydrocarbons, which are they're carcinogenic, they're harmful. Benzene, by the way, by itself is also carcinogenic. But when you have benzene as a part of a larger molecule, it is not. For example, these examples here. But coal is a complicated mixture of hydrocarbons, including many aromatic rings, a lot of the times other components, sulfur. So when you hear about clean coal, that is usually coal that is low in sulfur content. It doesn't mean that it makes less CO2 when it's burned or anything like that. It's really a misnomer. There's no such thing as clean coal when it comes to the environment, or burning anything makes CO2, and it's just not good for our climate. A real big problem that humanity will be facing over the coming decades and hopefully facing with success. Otherwise, an extinction event worldwide is possible, and that would include humans as well if we don't solve that problem. But here's what an example of what coal would look like, just a piece. Of course, there's lots of variety in the details of the structure. When it comes to naming benzene derivatives and aromatics, the parent name will be benzene, except for there's many accepted exceptions to this that you're going to have to memorize, unfortunately. Another one of these, you have to learn the vocabulary if you want to know the language, right? This is that vocabulary. So we have here chlorobenzene, nitrobenzene if the nitro group is on it, ethylbenzene if we have an ethyl substituent. But for many substituted benzene, as I mentioned, they have their own names. This includes methylbenzene. It's not generally called methylbenzene. It's almost always called toluene. If you have benzyl alcohol, it's never called that. It's always called phenol. And phenol has special properties to it. If you have a methoxybenzene, it's not called that. It's called anisole. Benzamine is not called benzamine. It's actually called aniline. Benzamine is a name that sometimes people use, though, as well. If you have a carboxylic acid group attached to the benzene ring, it's called benzoic acid. An aldehyde group attached to the aromatic ring, it's called, or the benzene ring here, it's called benzaldehyde. If you have here a ketone, it's called, with a methyl group on the other side, so that would make it a ketone instead of an aldehyde, it's called acetophenone. And if you have an alkene attached directly to the benzene ring, it's called styrene. You can think of polystyrene. Polystyrene is a polymer made from many styrene groups. if you have a substituent ring that is actually larger than the ring, it has 7 or more carbons. Actually, the benzene ring will be the substituent in this case, and the parent chain will be, in this case, the carbon chain here. So this carbon chain contains 1, 2, 3, 4, 5, 6, 7 carbons. So it becomes a parent chain since it has more carbons. So the parent chain here is hept for 7, ane for all single bonds. And as a substituent, the benzene ring will be called a phenyl group. So on the first carbon here, if we number them this way, this being the first substituent, 1, 2, 3, 4, and so on, this would be 1 phenyl heptane. Heptane being, so this part being the heptane right here. Heptane. And this part right here being the phenyl substituent. And so oftentimes, if we want to further condense the structure and make it easier to write, we will replace the phenyl groups with a pH, or this phi symbol here, which is representing benzene rings. So here we have tetraphenyl, 4 benzene rings, cyclopenta, that's the main chain here, cyclopentadiene, 2 alkene groups here, and then one for a ketone. And we'll talk about how to name ketones when we get to the ketone chapter, but their names end with one. And so when you have this, you could simplify it by writing all of these benzene rings as pH for the phenyl group. There are also names that are commonly used for dimethylbenzenes. If they're all called xylene. And also there are special names for substituents on locations on a benzene ring. So if we have a benzene ring here with 2 substituents and those are next to each other, we say that they are in the ortho position. So if they're 1, 2 substituents, we can instead say ortho. If they are one away from one another on the benzene ring, we call those positions meta. And if they are on opposite sides of the benzene ring here, we call those positions para, so the 1, 4 positions. And so these would be the IUPAC name technically, 1, 2 dimethylbenzene, 1, 3 dimethylbenzene, 1, 4 dimethylbenzene, but these are very, very commonly called xylene, ortho, meta, para. And this can be used for other substituents as well, not just methyl. So here we say the parent, and then we're counting here on the parent name. So if you have one of these special parent names, for example, remember that if we have a methoxybenzene, that is actually called anisole. And then if we add a nitro group to that, we can say 2-nitroanisole, this being the 1, here being the 2, or we can say ortho-nitroanisole, meaning that the nitro group is right next to the methoxy group. Here we have bromotoluene, so the parent chain here is toluene or methylbenzene, almost always called toluene, and we can call this carbon number 1, 2, 3. So this could be called 3-bromotoluene, or it can be called meta-bromotoluene. And here the parent name is benzaldehyde because there's an aldehyde directly attached to the benzene ring. The chloro group is in the opposite position as the aldehyde, so we can call this para-chlorobenzene or 4-chlorobenzene, 1, 2, 3, 4. So in terms of naming aromatic rings, we identify the parent chain. That will usually be the benzene ring, but if we have a longer hydrocarbon chain after that, it could be the larger chain. If there's a chain larger than 6 carbon atoms attached, that would be the parent. We identify and name the substituents. We number the parent chain, assign a locant to each substituent, give the first substituent the lowest number possible going around the ring, and list the numbers substituents before the parent name in alphabetical order, ignoring prefixes. So normal rules, just watch out for the parent chain. So here, remember there's lots of unique parent names for substituted benzenes. So here we can recognize that we have a benzyl alcohol here, which is called phenol. And then we have bromo substituents here. And it doesn't matter which way we number here. It will be 1, 2, 3, 4, 5. Or if we go the other way, it would be the same. It would be 1, 2, 3, 4, 5. So either way, we're going to have two bromos, and so we're going to say dibromo, and they'll be on the third and the fifth carbon. So this would be, its parent name would be phenol, and then either way we number, we have two bromos, we say dibromo, and there's no space here, so dibromophenol, and then we'd indicate the locations, 3, 5 dibromophenol. That's how we would name it. That completes it. We find the substituents on the third or fifth carbon here, third and fifth. We put the dibromo here for two bromo groups, and then 3 and 5 are the locations. Here's a couple of other ones. So these have been kind of labeled for you. Notice the black is highlighting here the the parent chain. So these were actually, we just went through them, but just to make sure that you can name them, I would go and pause this video and then restart it after you've named them. So you can pause now, and then I'll explain. Okay, if you've paused, I'll now explain these. So here we have 1, 2, 3, 4. This parent chain is called benzaldehyde, and the chloro is on the fourth position, so we can say 4-chlorobenzaldehyde. We could also say para-chlorobenzaldehyde or para, either one. Here the parent chain is toluene. Toluene, that would be this right here. And on the third carbon, 1, 2, 3, we have a bromo, so we'd say 3-bromo toluene or meta-bromotoluene. Here the parent name is called anisole, and this would be 2-nitroanisole or meta-nitroanisole. So you saw those ones before. Hopefully you can duplicate that. Oops, and my head is in the way. 2-nitroanisole, like, and that's how you name these ones. So for benzene, benzene was kind of a mysterious molecule in the late 1800s. In 1866, a guy named Kekule proposed that the benzene ring is composed of alternating double and single bonds, and proposed that there was a equilibrium between these two positions where the double bonds were here in this position and they switched with the single bonds over here. In reality, resonance was not known at that time, so in reality it was discovered that actually all of the bonds are the same. Really, they're the same all the way around. The real structure is somewhere in between these two structures. So now we know that the two drawings are resonance contributors rather than an equilibrium. And oftentimes you'll see a benzene ring written as a hexagon here with a circle in the middle. That is to represent that really, if we're looking at this benzene ring, it's really like each of these is a 1.5 bond, right? 1.5 bond, 1.5 bond, 1.5 bond, 1.5 bond, all the way around. And so a simplified way of writing that is to simply put a circle in the middle, showing that those electrons are evenly distributed around the ring and can move around. Aromatic rings, the pi bonds that are in aromatic rings are not the same as the pi bonds in an alkene. They do not readily undergo addition in the same way. So if you have an alkene here, this will readily undergo addition. Here with halogenation, you'll get an anti-addition of two bromine atoms. Hopefully you remember that mechanism that goes through a bromonium intermediate, right? So the intermediate here, we have the bromine that's like right here, and so it blocks the top side attack here, and so the remaining bromine has to attack from the bottom, and that's why we get this anti-addition. Knowing that mechanism is really important, knowing that it goes through the bromonium intermediate, so you can understand why you get the result that you do. Now, if you try to do the same thing with an aromatic ring, it's not going to happen because, as we were mentioning, these aren't really double bonds in the same sense as a alkene is a double bond. These electrons are completely In a conjugated pi bond system, they can move around freely between the unhybridized p orbitals all the way around this ring. And so they're not locked into a particular position like they would be in an alkene. And so they don't react in the same way that an alkene would. They're remarkably stable, and the bonds are hard to break. Now, if we were comparing to an alkene, we could determine how much energy, we can compare the stabilities of these. We have in the past by comparing the stabilities by the enthalpy of combustion. Instead, here we're going to compare the enthalpies of hydrogenation. And so when we hydrogenate this alkene, we recover 120 kilojoules per mole and get the cyclohexane ring. If we do this with two double bonds here in this cyclohexadiene here, 1,3-cyclohexadiene, we would get 232 kilojoules per mole, so slightly less per double bond. If we were expecting to hydrogenate all three triple bonds in the same way, we would expect the energy to be up here. We would get, approximately 3 times this energy, or around 360 kilojoules per mole, maybe a little less. But we actually observed that we would get a lot less if we somehow were to hydrogenate, which we can do under very rough conditions. We can hydrogenate all of these double bonds and get cyclohexane, but we'll only get 208 kilojoules per mole. So this is telling us that this benzene ring is much more stable than a theoretical cyclohexatriene here. It's not. It's a different type of molecule. It's much more stable as a benzene ring due to those conjugated pi bonds all the way around the ring. When it comes to molecular orbital descriptions, so remember, we have two ways of describing this bonding. We can use valence bond theory, in which we talk about unhybridized p orbitals, and each of them containing one electron here, and those electrons can move very around the ring. This is the valence bond theory perspective. So each carbon here being sp2 hybridized, therefore having one unhybridized p orbitals, which is pictured here, and each of those p orbitals has one pi electron in it, and they can move around. So in molecular orbital theory, what we do instead is consider that those 6 unhybridized p orbitals combine into making 6 molecular orbitals. The lowest energy molecular orbital, similar to what we saw in chapter 16, it covers the entire molecule, the entire benzene ring here, and it's very, very stable. Those electrons are free to move anywhere in there. Our next lowest energy bonding molecular orbitals will have a node in them, okay, and then the next lowest energy molecular orbitals will have 2 nodes in them, and then the highest molecular energy orbital will have 3 nodes in it. The lower 3 energies are the bonding molecular orbitals. The higher 3 energies are anti-bonding molecular orbitals. Since we have 6 electrons in our 6 p orbitals, in molecular orbitals, the first 2 will go in the lowest energy, most stable molecular orbital that covers the entire ring. The remaining 4 will go in the next higher energy orbitals here with a single node in them. And so notice that all of these electrons are paired up, and all of them are in bonding molecular orbitals. So this contributes to exceptionally strong bonds in the benzene ring from a molecular orbital perspective. And this helps to explain the exceptional stability of the benzene ring in a molecular orbital fashion and in a valence bond theory type of fashion. So we see that this leads to, but particularly the molecular orbital picture gives us a really good look at how this benzene ring results in exceptional stability relative to, for example, cyclohexadiene, as we saw earlier here, even more stable than cyclohexadiene. The locations of the nodes in the molecular orbitals determines their shape. Again, the determination of these molecular orbitals are based on high-level mathematical calculations. So these come from the averaging of the wave functions that describe each of these electrons. When you average them out, you get these variety of orbitals depending on their relative energies, and that's what determines the shape and the nodes of these molecular orbitals. You do not need to know how to do those high-level mathematical calculations. You can simply appreciate the results of them, which describe the shapes of these orbitals, which are also confirmed experimentally by basically running a negative probe across and seeing where the electrons spend most of their time. We can end up visualizing these nodes because there will be no electron density in nodes. And so these molecular orbitals are both theoretically confirmed and experimentally confirmed, and are probably the best picture of what's really going on with the electrons, although because of the mathematical complexity, they're perhaps not as instructive as considering valence bond theory. So the delocalization of the 6 pi electrons in the 3 bonding molecular orbitals accounts for that exceptional stability, as I was mentioning. So it's important to note that although benzene has this aromatic stability, not all fully conjugated rings have this. For example, cyclobutadiene is not considered aromatic. It does not have a spectacular stability that a benzene ring does. Neither does cyclooctatetraene. So cyclo, circle, octa, 8 carbons, tetra, 4 double bonds, tetraene. Tetraene, 4 double bond. So unlike benzene rings, cyclobutadiene and cyclooctatetraene will participate in addition reactions because their alkenes here are similar to another alkene that's not involved in an aromatic ring, because these do not have that special aromatic stability. So you will have the anti-addition of bromine very easily to cyclobutadiene or cyclooctatetraene. In addition, 2 cyclobutadienes can dimerize and react with one another in a reaction that is a essentially a cycloaddition type reaction, in which here you get a formation of a sigma bond. So these pi electrons go into the formation of a sigma bond between this ring and a sigma bond in this ring, leaving a double bond here. At that point, you can have a rearrangement that involves the breaking of the sigma bond to produce a pi bond. And so the pi bond that's produced right here, that is now this pi bond. And now these sigma bonds are no longer there. This one's this pi bond here, and the sigma bonds are no longer there. So there is a kind of equilibrium here that favors this cyclooctatetraene. If you leave cyclobutadiene in a bottle, for example, it will over time undergo this reaction and produce a cyclooctatetraene via a pericyclic reaction of this kind. So if cyclobutadiene and cyclooctatetraene are not aromatic, and the benzene ring is, why is that? And how can we determine if a ring is aromatic or not? Well, first of all, an aromatic ring, it has to meet not just one criterion. So it can't just have a fully conjugated ring with overlapping p orbitals, because cyclobutadiene has that, cyclooctatetraene has that, but they are not aromatic in the same way that benzene is. So the second condition is it has to meet the so-called Hückel's rule, and that is that an odd number of electron pairs, or 4n plus 2 total pi electrons, are present. So what we can see here is if we have, if we have a benzene ring like this, we can see that we have 6 unhybridized p orbitals here. This is going to give us 6 electrons here. 6 electrons, or 3 electron pairs. 6 total p orbital electrons, or 3 electron pairs. And so that will meet Hückel's rule. However, if we look at cyclobutadiene, there's going to be 4 pi electrons. That's going to be 2 electron pairs, and so that does not meet Hückel's rule. Likewise, here there would be 8 pi electrons. This would be 4 electron pairs, not meeting Hückel's rule. Or we can do it in the other statement here, that the total number of electron pairs here, if we do 4 times 1 plus 2, that is 6 electrons here. And so that is consistent with benzene here. If we do 4 times 0 plus 2, that would be just 2 pi electrons. That is not consistent with cyclobutadiene. The next one would be 4 times 2 plus 2. That would be 10 pi electrons. So if there are 10 pi electrons, that would work as well, but that is not consistent with cyclooctatetraene. So these compounds do not follow Hückel's rule. Now, we can explain Hückel's rule using molecular orbital theory. So let's say we are considering the molecular orbitals for cyclobutadiene. It's got 4 pi electrons and 4 unhybridized p orbitals, and so those are going to make 4 molecular orbitals when considered within molecular orbital theory. So we have 4 pi electrons here, 1 in each p orbital, right? As from the valence bond theory perspective, we got 4 pi electrons. We're going to get 4 molecular orbitals. 1 will be lower in energy. It will be a bonding orbital. 2 will be non-bonding orbitals, neither bonding nor anti-bonding. And the highest energy orbital out of the 4 will be the anti-bonding orbital. So in this case, the two of the electrons would go in the lowest energy bonding molecular orbital, and then 2 would go in the non-bonding molecular orbital. So overall, we don't have any additional bonding due to these pi electrons. And so that means that we don't have that extra aromatic stability that we had. If we go back to the molecular orbital picture for benzene, we can see that all of the electrons lie in bonding orbitals, so contributing to particular strength in those bonds. So there's going to be these are going to be extra specially strong bonds here that are created as a part of these molecular orbitals. However, in the case of the cyclobutadiene, this is not the case. We have 2 in the bonding, so we have a little bit of extra bonding stability, but these do not contribute at all to the bonding. Also, they are unpaired, and this is what we're going to call an open shell or not closed shell molecule, meaning that it has unpaired electrons in its molecular orbitals. We call molecules that are not closed shell like this, that are open shell with unpaired electrons, we call those anti-aromatic rather than aromatic. We can perform a similar type of analysis with cyclooctatetraene. So its molecular orbitals would be situated such that, well, first of all, we have 8 pi electrons, 1 in each of these p orbitals, so 8 pi electrons. And its molecular orbitals will be such that 1 will be the lowest in energy, then there will be 2 that are equal energy higher than that, another 2 that are equal energy higher than that, another 2 equal energy higher than that, and then finally a highest energy orbital. Those bottom 3 here are considered the bonding orbitals, the middle 2 are non-bonding orbitals, and the top 3 are anti-bonding orbitals, higher than energy than the individual unhybridized p orbitals here. And we have 8 pi electrons to distribute. The 2 go into the lowest energy bonding orbital. The next 4 go into the higher energy bonding molecular orbitals. And then we can see the last 2 have to go into the non-bonding orbitals. So again, we have an open shell molecule with unpaired electrons in the molecular orbitals. So cyclooctatetraene is also considered anti-aromatic. Now, one thing to note is that just like when we were talking about cyclohexane, how it can adopt multiple conformers, these larger rings can also adopt multiple conformers. For example, we can have a boat-type structure, a boat-like structure, or a tub-like structure for cyclooctatetraene, and when it adopts that structure, there's really no sideways overlap between the p orbitals, really. So we do not have conjugation in that sense. Remember, conjugation appears due to the sideways overlap of many unhybridized p orbitals. None of these have a sideways overlap, so there's no conjugation at all. Thus, the system is neither aromatic nor anti-aromatic. It is not conjugated. It is non-aromatic. So in order to predict the relative energies of these molecular orbitals, we obviously can't go and do a quantum mechanical calculation. That would require a computer. Finding the exact energies of these orbitals is a very complicated calculation. It, in fact, can't be done analytically. In fact, you can't figure out exactly the results of these calculations. You at best do approximations. And in recent times, our approximations of the energies of these molecular orbitals has gotten better and better and better with more powerful and sophisticated computers and calculation algorithms. However, this is a very simple process that we can use to estimate the relative energies and their energy, whether those orbitals represent bonding molecular orbitals or anti-bonding molecular orbitals. And the way in which it's done is we start with a circle, and then we inscribe the polygon with however many carbons exist in our ring, making sure that at the bottom, the bottommost carbon points straight down. Then, at that point, for each intersection, we indicate a molecular orbital. So there'll be one at the very bottom where that one or two lowest points are. There will be two above that, and then two above that. And then if we have two intersections here at the same level, we'll have two. If there's one pointing up, we'll have another one there. What we do is we bisect this, draw a line right in the middle. So here, through the center of the circle. So the center of the circle would be right here. So we end up with three bonding orbitals for, this would be cycloheptatriene, most likely, if we had a triene in here. We see that three lines lie below that bisected line in the circle. Four lines lie above it, four orbitals. And so those three orbitals below the line are the bonding orbitals, and the four above the line are the anti-bonding orbitals. And then we can determine how many pi electrons exist in our molecule and put those in the molecular orbitals. So here are the way those frost circles will look for rings of each size here. If we have a four-membered ring, there will be one bonding molecular orbital, two non-bonding orbitals, and one anti-bonding orbital. If we have a five-membered ring, there will be three bonding orbitals and two anti-bonding orbitals. If we have a six-membered ring, there will be three bonding molecular orbitals and three anti-bonding molecular orbitals. We just saw the seven-membered ring example with three bonding molecular orbitals and four anti-bonding molecular orbitals. With an eight-membered ring, like we saw in Cyclooctatetraene, we would have three bonding molecular orbitals, two non-bonding molecular orbitals, and three anti-bonding molecular orbitals. With a nine-membered ring, we'd have five bonding molecular orbitals and four anti-bonding molecular orbitals. And with a 10-membered ring, we'd have five bonding orbitals and five anti-bonding orbitals. Note that the number of bonding orbitals is always an odd number. And so aromatic compounds will always have an odd number of electron pairs here. So let's start to analyze other aromatic compounds. Remember that aromatic or non-aromatic, and determine if they're aromatic or not. Remember that aromatic compounds will have fully conjugated ring with overlapping p orbitals and will meet Hückel's rule, meaning they have an odd number of electron pairs, or 4n plus 2 total pi electrons. In anti-aromatic compounds, they will fulfill two criteria. They will have a fully conjugated overlapping p orbitals. If they don't have that, they're considered neither aromatic nor anti-aromatic. They will have an even number of electron pairs, or 4n total pi electrons. When a compound fails criteria 1, again, it is called non-aromatic. It's neither aromatic nor anti-aromatic. So here are some examples of other aromatic rings. For example, we have the benzene ring here. If we have larger aromatic rings, we can call these annulenes. Annulenes are rings that are fully conjugated. So benzene could also be called 6-annulene, meaning an annulene where we have 6 carbon atoms. Here's an annulene with 10 carbon atoms, all conjugated, right? Double, single, double, single, double, single, double, single, double, single, all the way around. Also conjugated here, it's double, single, all the way around with 14 carbons. Is called 14-annulene. Anilines can be aromatic, anti-aromatic, or non-aromatic. We should apply our conditions that we saw here to determine whether they are aromatic, non-aromatic, or anti-aromatic. So for example, let's say, and that is to say also that aromatic rings do not have to be neutral. They can have carbanions or carbocations, and that may contribute to their aromaticity. So for example, consider if we have a 5-membered ring, okay? That 5-membered ring, remember we draw a circle. So just to kind of repeat what's here, we draw a circle, and then we put a pentagon in the ring, and when we do, we make sure that we have the lowest one carbon, at least 1 or 2 carbons facing straight down, right? There has to be a carbon facing straight down, rather not 1 or 2, just 1. So 1 carbon facing straight down, then we write the rest of the structure. Okay, so this gives us, and then we bisect the circle. So we go right through the middle here, so just like we did here, right through the middle of the circle. And at each intersection, we have a molecular orbital. 1, 2, 3 bonding, 1, 2 antibonding right here. So 1, 2, 3 bonding, 2 antibonding. Okay. So we have 3 bonding molecular orbitals that can accommodate 6 pi electrons. So in order for this compound to be aromatic, there must be 6 pi electrons existing in this molecule. Because remember, when we look at Hückel's rule, we have 4n plus 2. So if the n is 0, that would be 2 electrons. If the n is 1, that's 6. So we'd have to have 6 here for this to be an aromatic ring. So how might we have 6? Let's think about it. If we have a regular cyclopentadiene, there will not be 6 pi electrons. There will in fact be 4 pi electrons. One in because we have this carbon is sp3 hybridized with no unhybridized p orbital. These carbons are sp2 hybridized, sp2, sp2, sp2. So those are all going to have one unhybridized p orbital with an electron in it. So that's going to be 4 pi electrons. So this does not have 6 pi electrons. However, if we had a carbanion here instead of a hydrogen, well, now we would have an allylic lone pair, which would result in resonance throughout the ring. And so this would be a part of the, and at that point, this carbon would then be sp2 hybridized, and we'd have an unhybridized p orbital here containing 2 electrons. So these electrons are delocalized, right? These are delocalized electrons. They are going to be delocalized electrons. These are going to be in an unhybridized p orbital, and they will move around the ring. We know that because they're an allylic lone pair and they're not currently involved in a pi bond. So remember that allylic lone pair, we can get resonance here. So the allylic lone pair is a 2-arrow resonance pattern, and so that's going to give us this resonance structure here now, where we have a pi bond here. This is the new pi bond, and now we have the lone pair right here, and this is also allylic, and so we have this resonance structure where now we have the pi bond here, and we have a lone pair here, and now it's allylic lone pair again, and so we have again a two arrow resonance arrow situation here, and now we have a new pi bond that wasn't here before. And now we have another allylic lone pair here, and this continues to go all the way around the ring. It will continue, right? And so now we have the new pi bond that's right here. And if we do this one more time, we will actually arrive back at the beginning. That will consider all structures. Whoops. Erase. I meant to say that we are, this goes around that without covering the word here. So notice that there's an exceptional stability to this carbanion compared to a standard carbanion because of all of this resonance. And so remember that when we were using ARIO before, to evaluate the stability of the conjugate bases of acids, when we look at this, in terms of atom, it's not so good. Carbon Not so good, right? Oxygen would be better. However, in terms of resonance, the resonance is really awesome here. Normally, if we had an allylic proton, the pKa for that would not be super low, right? It would be pretty high still. However, it would be greater than it would be like in the 20s or so. However, because when we deprotonate this, so if we have this react with hydroxide, for example, and do a proton transfer, now what we have is this carbanion. And this carbanion has exceptional resonance stability. So we would say that this contributes to the stronger acidity of this cyclopentadiene, and we can see that it is on the order of the acidity of water, which is much more acidic than we would consider normally a normal sp3 hybridized carbons. For most sp3 hybridized carbon, if we just had a normal methane, for example, this pKa would be like 50, about 50. And so we can see that this contributes significantly to the potential acidity of these protons. Here we have a 7-membered ring. Okay, so if we inscribe the 7-membered ring into this circle, again, we make sure that the bottom part of the ring points down, and then we draw a molecular orbital at each intersection here. And so like that gives us 7 molecular orbitals from the 7 unhybridized p orbitals in this molecule. And then we draw a line right through the center, and we can see that for a 7-membered ring, we have 6 bonding molecular orbitals and 4 anti-bonding molecular orbitals. So again, we're going to need 4 times 1 plus 2. We're going to need 6 pi electrons in order to have a aromatic ring. Those are going to occupy all of the bonding molecular orbitals. This can occur if we have a cation in our ring. So let's consider that. If we have a 7-membered ring, like this, and it has 3 double bonds, well, this is not going to be aromatic normally, okay, because it's not conjugated all the way around, right? However, if this is a carbocation, so we have just one hydrogen here, and this carbon is sp2 hybridized, then we will have an unhybridized p orbital here, and we will have unhybridized p orbitals all the way around the ring. And so that will cause it to be aromatic at that point. And we see that here this is a carbocation, so there are no additional electrons here. So our 6 pi electrons come from these 6 carbons here, each one contributing 1 pi electron for a total of 6. So we can see the way that works by looking at the resonance structures. So here we have an allylic carbocation. Remember, allylic carbocation resonance arrow is a single resonance arrow situation. Remember, there's only one hydrogen here. So then when we move that pi bond, this carbon has one bond to hydrogen, 2 bonds to carbon, and no lone pairs. So it's sp2 hybridized with a positive formal charge here. And this would go all the way around the ring. 7, we'd have 7 resonance structures here. So this happens to be called the Tropylium Cation. You don't need to remember that name at all, but it is an aromatic cation due to the presence of its 6 pi electrons and its conjugation all the way around the ring. So we've met both conditions. Conjugation all the way around the ring due to the fact that this carbon is sp2 hybridized. Note that if this were not a carbocation, this carbon would not be sp2 hybridized, and therefore you would not meet condition 1. You would not have conjugation all the way around the ring, so you would have a non-aromatic. But since we have a carbocation here, this carbon is now sp2 hybridized. We have p orbitals on every single carbon unhybridized, and so the electrons can travel all the way through. This is conjugated, and there will be 6 pi electrons, 1 from each of these carbons here, and none from this carbon right here. So that obeys Hückel's rule, 4n plus 2. 4 times 1 plus 2 is 6. In terms of rings that do not only contain carbon atoms. We call these heterocyclic, meaning they have another atom that's not carbon, such as nitrogen or oxygen in the ring. And when we do that, we have to consider when we have one of these, we have to consider whether the lone pair here that exists is part of the conjugation or is not. Is it in an unhybridized p orbital? So in the case of pyridine, for example, the lone pair here is in a hybridized, sp2 hybridized orbital. And we know this because the p orbital is already involved in a pi bond here. Right here, it's this pi bond here is the sideways overlap of these p orbitals. There is an unhybridized p orbital on each of these carbons and on the nitrogen, and they are all involved in the conjugation here. And so this lone pair must occupy the sp2 hybridized orbital and is therefore localized. It's not delocalized. However, the situation is different with pyrrole. Here in pyrrole, this nitrogen is also sp2 hybridized. However, this lone pair is not involved, or rather is involved in the conjugation here, because the unhybridized p orbital is available to contain those pi electrons, whereas here it was involved in the pi bond. Here it is not in this situation. So here we have one electron here involved in this pi bond here, and the lone pair over here. Here the lone pair is in an unhybridized p orbital, so it can be involved in this. It is delocalized, and it can be involved in this conjugated ring here. So if the heteroatom's lone pair is necessary for aromaticity, it will be included in the number of Hückel pi electrons. So in this case, it is not necessary for the aromaticity. It is in the hybridized orbital, but in the case of the pyrrole, it is involved. So our number of pi electrons are basically, we have one electron in each of these four sp2 hybridized orbitals. Then we have the additional two in this lone pair. So that's a total of 6 pi electrons, which obeys Hückel's rule, 2 times 4 plus 2. And so that would be 6. And so the ring here in pyrrole is aromatic. These electrons are in the pi bond there. If the lone pair is necessary for aromaticity, then the lone pair will not be as basic, because it's going to be spread out and delocalized across the entire ring. So in the case of the pyridine here, this nitrogen, it has a localized lone pair, so that is quite basic. And so we can see that it can accept a proton and make this protonated nitrogen with four bonds, no lone pairs. So this is a positive formal charge. So the pKa of this as an acid would be 5.2. Whereas in the case of pyrrole, it's not as good of a base, because when we add the proton here and we have the nitrogen making 4 bonds with with no lone pairs here, that's a positive formal charge, and the pKa here is much lower, meaning that this is much more acidic, meaning the conjugate base is a much weaker base. And so that is because these electrons are not just on this nitrogen, they are spread out through the entire ring. This can be visualized better if you look at the electron density map, and you can do this on MolView, for example. MolView, I don't know if you guys remember, that's a nice little program that I told you guys about earlier for doing molecular structures, and you can actually tell it if you choose JMol, and then you choose on the menu, you can build the molecule JMol, and then you use MEP. You can see this electron potential mapping. What you'll see here is that in the case of pyridine, the electrons are very localized next to the nitrogen. The rest is green, representing a lack of electron density. Whereas in the case of the pyrrole, the electron density is pretty even throughout the ring because those electrons are delocalized across the ring. Just to kind of demonstrate for you here, if you go to MolView, here, you can take a look at any of these for yourself if you want to see the localized or delocalized. This is a really good way of verifying for yourself this kind of conjugation or aromaticity or not. So you can see here, if I choose JMol and the MEP surface lucent, we will see that that electron density here is very localized around the nitrogen, whereas if we get rid of that and we do here, let's see, I'm going to do this, we do the other structure there, the pyrrole, we'll see that the electron density is spread throughout the ring. So this is a great way to check the aromaticity. You can see that those electrons are delocalized around the aromatic ring. And there's a lack of electron density here because the nitrogen is electronegative, pulling the electron density away from hydrogen. So I think that's where I'm going to end with this video. For the next video, we'll continue to talk about larger aromatic rings, and we'll finish off this chapter. I'll see you in the next one.